All right, welcome everyone. I'm Avinash Tongre. I'm at the University of Connecticut. Today we have the review session for lecture 11 on hydrodynamic instabilities. And we have Dr. Bruce Remington from Lawrence Livermore, who's going to be taking over and addressing the homework questions that we had posted on Monday. So you can take over, Bruce.
And you want me just to go through the problems, not the view graphs again, right?
Yeah, mostly with the problems in this. I have some questions related to the problems that we can discuss.
Can you see my view graph?
Not yet.
That's not a good sign. How about now? Can you see them?
No. Are you able to share the content?
I think I am sharing. Share content.
Yeah, now we can see them.
Okay, good. Okay. And can you still see that?
Yeah. Would we see a few other things as well? I think you're sharing your desktop. So if you can go into slideshow or something, I think that would be good.
So I'm in slideshow right now, but you're still seeing my desktop.
No, it's just a little delayed, I guess.
Oh, good.
Yeah.
Okay. Okay, so this is the problem set with the solutions that I'll talk through.
Mm-hmm. Okay,
the first question was, in a direct drive laser illumination Rayleigh-Taylor experiment, assuming 1/3 micron laser light incident on a planar package that's 5 microns of plastic glued to a 10 micron rippled vanadium, give the ablation pressure in units of CGS units of ergs per cubic centimeter and megabars also, and the conversion from megabars, 1 megabar is 100 GPa, which is 10 to the 12 ergs per cubic centimeter. And the formula to use is a formula from a John Lindell paper in 1995 that gives the ablation pressure in megabars as 40 times the ratio of laser intensity to wavelength to the 2/3 power, where the laser intensity is given in units of 10 to the 15 watts per cubic centimeter, watts per square centimeter, and the wavelength in microns. And so the equation, the answer here, the ablation pressure in megabars is 40 times that ratio of intensity to wavelength to the 2/3 power. Inserting 4 times 10 to the 12 watts per square centimeter in units of 10 to the 15 watts per square centimeter is 0.004. Divided by 1/3 micron, that quantity to the 2/3 gives 2 megabars, 2.1 megabars, which is 2.1 times 10 to the 12 ergs per cubic centimeter. Any discussion or questions about that, or should I just go forward and go through these? I'll continue on. Calculate the acceleration of a target where the target is assumed to be a 5 micron plastic ablator glued to a 10 micron vanadium foil, metal foil, assuming rigid body motion, so ignoring compression waves and rarefactions. The ambient density of plastic and vanadium are 1 gram per cubic centimeter and 6.1 gram per cubic centimeter respectively. Give the answer in centimeters per second squared and also microns per nanosecond squared. I keep doing these conversions because the equations are usually given in CGS, but the experiments that we do we typically are dealing with microns and nanoseconds. Let's see, assume that the laser does not burn off a significant fraction of the CH ablator, then you can write Newton's second law, F equals ma, normalized by the area on both sides of the equation. That gives you the equation pressure equals areal density times acceleration, where I'm using G for acceleration. The areal density is the sum of two terms, the initial density of plastic times the thickness of the plastic, delta Z, Z1, and rho 1 times delta Z1, plus the density of vanadium, rho 2 times delta Z2, its thickness, that quantity times G, the acceleration. And so inserting the 2.1 times 10 to the 12 ergs per cubic centimeter on the left side of the equation equals on the right side of the equation the 1 gram per cc for plastic times 5 microns is 5 times 10 to the minus 4 centimeters, plus the ambient density of vanadium, 6.1 gram per cc times its thickness, which was 10 microns, which is 10 times 10 e to the minus 4 centimeters. That whole quantity times the acceleration. Solving that, plugging in the values gives an acceleration of 3.18 times 10 to the 14 centimeter per second squared. And you can convert that by using the conversion 10 to the 4 microns is 1 centimeter, and 1 second is 10 to the 9 nanoseconds. That quantity squared converts this into microns per nanosecond squared. So the acceleration is 3 microns per nanosecond squared, 3.18, which is slow, but that's what you get for this particular pressure, because the ablation pressure that I put into this problem was relatively low. Part C, 1C, calculate how far in microns the physics package moves at this constant acceleration over a laser pulse duration of 10 nanoseconds. So that's just distance is 1/2 gt squared, 1/2 times the acceleration, which is 3.18 micron per ns squared, times the time duration, 10 nanosecond quantity squared. So you can do this just by visually, and it comes down to 159 microns. The distance traveled matters for experiments, because if the distance traveled, first off, it's what drives the amount of Rayleigh-Taylor growth, but also the distance traveled compared to the transverse size of the foil determines whether or not you'll have a planar experiment or whether you start to bow and deviate from planarity. So we often are calculating distance traveled. Okay, that's questions 1, the 3 parts of questions 1. Question 2, calculate the Rayleigh-Taylor growth rate, gamma, for wavelength, lambda of 60 micron rippled wavelength, assuming linear regime Rayleigh-Taylor instability in the classical inviscid regime, meaning no viscosity or strength. The relevant equation is a quadratic, gamma squared plus 2k. So gamma is the growth rate inverse of time, inverse seconds. K equals 2 pi over lambda. That's the wave number of the perturbation, where lambda is the wavelength. Nu is the kinematic viscosity in centimeters squared per second. Capital A is the Atwood number, which is the ratio of the difference in density between the vanadium and the plastic divided by the sum of the densities. Okay, so calculate using those quantities and that dispersion relationship, calculate gamma, solve the equation. So assuming inviscid flow, that says nu, the viscosity, the kinematic viscosity is 0. So this is a big simplification, and the Rayleigh-Taylor rate equation simplifies to gamma squared equals AKG. Another simplification, I'm assuming that the Atwood number at pressure is reasonably close to the ambient Atwood number. So I'm assuming capital A equals capital A naught. So I can use ambient densities. So simply plugging in the density difference, 6 minus 1 in the numerator divided by 6 plus 1 in the denominator gives an Atwood number of 0.718. And so inserting this into the equation, the quadratic equation, it gives you, and then solving, gamma squared is 0.24 inverse nanosecond squared. So gamma, the growth rate, is 0.5 inverse nanoseconds. So it's growing relatively slowly, but still in a easily measurable amount. Part 2B, calculate the Rayleigh-Taylor growth factor for the 60 micron wavelength perturbation for a 10 ns drive. Again, assuming linear regime Rayleigh-Taylor and ignoring material strength and viscosity. So if you assume that the amplitude of the ripple is given by h, and that the initial amplitude is h naught, then h over h naught, that ratio is the growth factor. How much the ripple amplitude has increased in time. That's equal to e to the gamma t, where gamma is the Rayleigh-Taylor growth rate and t is the duration of the acceleration. And so h over h naught, the growth factor, e to the gamma t, we just calculated gamma at 0.489 inverse nanoseconds times time 10 nanoseconds. So that's e to the 4.89. That's 133. So that's a reasonable growth factor in terms of measurements that we make on lasers. Growth factor of 100-ish, about 100 is easily measurable and probably has not yet gone deeply nonlinear. 2C, recalculate the Rayleigh-Taylor growth rate, including the vanadium material strength, assuming this as a lattice viscosity for the moment. And so we're going to assume I believe it's a 400 poise initial lattice viscosity. The units of viscosity are dynes seconds per centimeter squared. That's also the same as grams per centimeter second. I give several references here for the Rayleigh-Taylor formula in the presence of viscosity. The dispersion equation is given again as gamma squared plus 2k squared nu gamma minus AKG equals 0. This time nu is 400 poise. And so we recalculate this. I'm sorry, nu is 400 poise divided by the density. I'm ignoring the density of plastic, its strength. I'm assuming its strength is small compared to the metal foil, so I'm dealing with just the vanadium. And so you can see that inserting the terms in the equation for gamma squared, so gamma squared equals 2 times the wave number, 2 pi over 60 microns, quantity squared, times nu, which is the dynamic viscosity, mu, divided by the density. So that's 400 poise divided by 6.1 gram per centimeter cubed, quantity times gamma, the growth rate, minus, and the constant term is 0.718 times 2 pi over 60 microns times 3.18 micron per ns squared. So that's the quadrant equals 0. So that's the formula you're solving. So it simplifies to gamma squared plus 1.44 gamma minus 0.24 equals 0. Inserting that into the quadratic formula gives you a gamma square, gives you a gamma of a growth rate of 0.15 inverse nanoseconds. So reasonably slow. Then the growth factor is e to the gamma t, so that's the exponent of 0.15 inverse nanoseconds times 10 ns. So that's e to the power of 1.5, which is 4.5. So that's a very low growth factor when you include the strength. So that comparing the growth factor with strength of 4.5 versus the growth factor without strength, which was 100 something. So you can see there's a very large difference when you put in material strength in the form of 400 poise. And the reason being is 400 poise is a very, very high viscosity, maybe orders of magnitude above what it would be in a liquid. Okay, 2D, the final piece of this part of question 2 is assume the strength sigma can be written as the square root of 6 times the average plastic strain rate times the dynamic viscosity mu. And so you say, why write this equation this way? Well, the physical intuition here is that if the strain rate, d strain, d epsilon dt, if the strain rate is high, the amount of time that you have to nucleate and transport dislocations is low, which necessarily means the strength is going to be high. That's why you get this linear dependence of strength with strain rate. And of course, mu times mu viscosity, if it's very viscous, of course, the strength will be high. So assume the strength that can be written as the square root of 6 times the strain rate times viscosity. And let's see, calculate the strength of vanadium under these conditions, where the strain rate is 10 to the 7 inverse seconds, which is a reasonable strain rate for these laser experiments. Calculate the strength for vanadium in kilobars. So the answer, plugging in sigma, the strength equals the square root of 6 times 10 to the 7 inverse seconds times 400 poise, gives you just about 1 times 10 to the 10 dynes per square centimeter, which corresponds to 0.01 megabar, which corresponds to 10 kilobars. So that's the strength calculated with this formula. Okay, question 3, now going to an actual model of material strength that we use, and it's widely used in the community. And I picked this because the problems that I'm giving in these values, they're not just textbook values, they are actual values from the research we're doing at the Livermore lab. So these are problems we actually work on, and these are models that we use day in and day out. So the Steinberg-Guinan strength model assumes that the strength is proportional to the shear modulus. And you can write the strength as strength Y corresponding to a yield strength equals its ambient strength, Y naught, times a factor proportional to the strain, 1 plus beta epsilon sub p. So that's 1 plus a constant beta times the plastic strain, that quantity to the power of n, times the second factor, which is 1 plus a, which is a constant, times pressure, divided by the compression. Eta is the compression, rho over rho naught, so divided by the compression to the 1/3 power, minus b, another constant, times the temperature minus 300 K. So the temperature in Kelvin minus 300 K. So there's a pressure term and a temperature term. As the pressure goes up, the strength goes up. As the temperature goes up, the strength goes down. And the whole thing is multiplied by a factor corresponding to plastic strain and the initial strength, where P is in megabar and T is in Kelvin. So using values from what we call the Steinberg Blue Book, or you can find there's a publication by Steinberg that gives these. I give all the values for the ambient density, 6 grams per cc, the ambient shear modulus, 0.48 megabar, and then the constants A, 1.02 inverse megabar, capital B, 2.06 times 10 to the minus 4 inverse Kelvin, beta, assume beta of 10, and little n of 0.1. So then the question is, assuming compression of 1.3, eta, or rho over rho not equal 1.3, at a pressure of 0.6 megabars, temperature 1000 Kelvin, and a plastic strain of 0.1, calculate the strength. And then compare this with what we inferred experimentally in experiments done at the Omega laser, shown on the right-hand side, where we did a fitting to the experimental data, which are the data points, where the fitting parameter was the viscosity, dynamic viscosity in poise. And the best fit to the experimental results were of a viscosity of 400 poise. So inserting the quantities that we know into this equation, there's a long equation there where I give Y in megabars, and the ambient, giving the ambient strength of of 6 times 10 to the 3 megabar, and so on. I won't read through all these values, but they're given in the equation and what's was sent around. And so the result of this is 9 kilobars. So the strength of vanadium at the pressure of 0.6 megabar, temperature of 1,000 Kelvin, compression of 1.3 is 9 kilobars coming out of a Steinberg-Guinan model. Now you come to the experiment where we actually measured this experimentally at the Omega laser under these conditions. And this is all written up in a physical review letters by Jesus Park, where I give the reference there, and the figure that matters I reproduce here on the lower right-hand side, showing the fitting parameter of viscosity and how we fit that to the experiment and came up with 400 poise. So that leads to an experimentally inferred strength of 29 kilobars compared to the prediction by the Steinberg-Guinan model above of 9 kilobars. So the prediction by Steinberg's model is a factor of 3 lower than the experimentally inferred strength from the experiments. And so then the question, and this is a real result, and the question is, what is the possible difference? Why is there this big difference? And this is a real question that we still work on also day in and day out. Why do the experimental strengths we measure seem high compared to predictions oftentimes? And so I just list a number of possibilities that come to mind, and these are issues we are actually currently working on. So what could be the cause of these differences between what we see experimentally and what we predict with a simple theoretical model like Steinberg? The first that comes to my mind, is the Steinberg strength model does not take into account strain rate. So strain rate hardening in the experiments, due to the high strain rates that we have on laser experiments, it's about 3 times 10 to the 7 inverse seconds. That's a very high strain rate. There's not much time for the material to nucleate and transport dislocations. One might also be possibly in the phonon drag regime as opposed to thermal activation, and the drag coefficient could be high. So that's one possibility. Another is that the Steinberg-Guinan shear modulus prediction is simply wrong at these megabar pressures, which is quite possible. Another possibility is there might be phase transitions in the vanadium, whereas the Steinberg-Guinan parameters were set for the ambient phase at a megabar or close to a megabar. It may have gone through a phase transition. So if the phase is different, then all of the thinking that went into the coefficients of the Steinberg model would have to be rethought because the lattice is different. Let's see, and a fourth possibility, this one might be more remote, but it's something that does come up, and we've talked about it in our research group. There's the remote possibility that the CH heat shield, remember the physics package that's being accelerated and is Rayleigh-Taylor unstable, is a plastic ablator glued onto a rippled piece of vanadium. So I've been focusing on the properties of the vanadium, but the CH heat shield, so the CH could come into play. We'll ignore H for a second, but under these high compression, high pressure, low temperature conditions, the carbon in the plastic possibly could turn into diamond. So what was a CH heat shield, just plastic with zero strength or close to zero strength, now is a mixture of diamond, solid state diamond, and hydrogen. And so now the properties of the heat shield would be very, very different and could no longer be ignored. And one might have to consider the strength of diamond in our prediction of the strength of this physics package. So that's an issue we actually are working on to try and decide, could that really be going on or not in our theory and simulations and experiments. And then here are the references that I've been referring to. The bottom reference is the Steinberg paper in 1980. And then from the top down, there's the paper about Rayleigh-Taylor equations with viscosity by Bellman in 1954. And then in context of our work at the lasers, Jeff Coleman paper 2003, if the basic equations for these laser experiments, not the strength work, but the plasmas, John Lindell, 1995, Physics of Plasmas, and a paper by Michaelian in 1993 and Heisuk Park in 2010. So that's it. Those are the answers to the questions. So is there any discussion or follow-up?
Yeah, Bruce, there have been a couple of questions in the text box. I don't know if you can read them. I can read them to you if you want.
Yeah, I don't see them.
Okay. So one question from Avnish is there any approach to calculate acceleration of target for higher intensity lasers? If the laser does burn the ablator, we only consider the mentioned case in the answers.
I didn't quite get that. Is there a plan to measure the acceleration of targets under what conditions?
For higher intensity lasers, so when you have lasers with higher intensities, could you have burning of the ablator?
Yes.
Okay.
And we do almost all of our experiments at higher intensities. Just to make this problem and bring it down to regimes that I thought might be a little bit more relevant to these discussions, I dialed the laser intensity down to a very low level, so it gave a 2 megabar pressure instead of, tens or 100 megabars.
Yeah.
So we typically do most of our research at higher intensities.
Okay. And then I had one question is based on the strength model. Is it possible to develop a strength model based on first principles?
Yeah, we've spent years working on what we call the multi-scale model, and the whole purpose there, and it took probably at least 10 years, I think, to develop that model, is to start from first principles, starting from density functional theory, write down what you think the forces are on dislocations, parameterize those, put those into, a dislocation velocity as a function of applied shear stress, put that into molecular dynamic simulations, calculate how the dislocations evolve, parameterize those so that you can insert them into dislocation dynamic simulations, and ultimately parameterize those results and insert those into hydrodynamics codes. So the Livermore multi-scale model, and there's other people that work on these multi-scale models, do exactly that. That's as close to first principles as we can get, and then we try, and now we can tear apart the individual physics pieces that go into that model and decide, are there places where we can do focused research to see whether the individual pieces that go into the model are correct. Well, they're never correct always, and so then the question is, where do they break down?
Yeah.
And what do we have to worry about versus not? And sort of day in and day out, those are the kinds of conversations that we have all the time.
Okay, great.
I mean, that's right at the center of our work.
Something?
That's a good question.
Bruce, could I add something to that?
Yeah, please do.
So in the chat box, Avinash referred to multi-phase material, which is another level of complexity.
Yes.
So there's some things that we can say about that. So that's been addressed at different levels. So kind of the simplest level was something that we did recently for high pressure lead. And so there it was developing one of these improved Steinberg-Guinan models where we use density functional theory to calculate the elastic properties of high pressure lead, which is in a BCC phase as opposed to the FCC phase that's at ambient conditions. And we predicted that the strength would be higher in that phase. And when the experiments were done, they were in remarkable agreement. And I think it was especially astonishing because lead was a case where there's extreme hardening, so that the strength at pressure is 250 times that at ambient conditions. And, in a commentary, someone noted, this is like the Hulk of materials, in everyday ordinary conditions, it's kind of weak, not very impressive, but you agitate it and it becomes super strong. So that's lead. It's kind of the Hulk, and but that's kind of a poor man's approach to strength modeling. And in many cases, there can be other things that happen across phase transformation. So that wasn't taking anything into account in terms of how the grain structure changes or what happens to dislocation density as it transforms from one phase to another. So there was an earlier attempt to develop a full multi-scale model for vanadium across the phase transformations that are to a rhombohedral structure. And I think it was an interesting exercise, and and it was possible to develop a description of the plastic flow in the different phases, but then kind of understanding exactly how to pass, say, the microstructure from one phase to another. I think it was very much dependent on the system. And I think it's a really interesting question. I think it's one I hope that people will address going forward of, if you generate dislocations in one phase and now you transform to another, are they still there? Do they get absorbed into, boundaries as the phase is changing?
Exactly.
And then the questions, do you end up with a much finer grain microstructure? Is the microstructure more highly textured because of that? So there are lots of really interesting questions, and I hope some of the students tuned in will take that up in their career and really understand what's going on in these systems.
Yeah, because we are running some simulations of copper iron composites, and our mission is running those. And what we see is iron will undergo a phase transformation, but when there's a reverse phase transformation, you actually see twinning for certain orientations. And so that for us is a little interesting as to how would somebody come up with, strength characteristics or strain hardening mechanisms when you have these complex features, either you have phase transformed regions or you have now distributions of twins.
Yeah.
Okay.
It's really interesting.
Very good. And I don't know if you have a few more minutes. I had one follow-up question. You had mentioned about strain hardening at high strain rates. So when you run laser interactions, it's not only high strain rate loading, but say, let's say you go to higher intensities, you also have very high temperatures that are generated. Does that affect the strain hardening behavior?
Yeah, it does. I mean, the question is, as you vary the temperature, but if you keep the material solid, so there's a lattice, now you can vary anywhere from a factor of 10 below the melt temperature up to, say 90% of the melt temperature.
Yeah.
And the effects can be large. And in particular, the deformation mechanism can change as a function of temperature, and you can move from thermal activation into phonon drag and back. And so we do vary the temperature intentionally as we're doing our experiments. One team of the team that I'm on, the strength team, has usually been trying to keep the temperature low, because in the beginning days when we were trying to develop the experiments, there was always the worry that we unintentionally melt the sample. So we got used to running with experiments where the predicted and measured temperatures were factors of 5 to 10 below melt. But now more recently, we're saying, well, we also want to turn the temperature up, but still keep it solid. To make sure we understand the temperature dependence and get closer to the melt curve. And so we're slowly inching our way in that direction.
Okay. Great.
There's always the concern that there's preheat from one source or another. So, I mean, we've gotten quite cautious, because you can spend a year just trying to track down a source of preheat. But things are much better controlled now than in the early days. So we're starting to get a little more adventurous as we try and try to intentionally raise the temperature as opposed to unintentionally.
Okay. Well, that makes sense. Very exciting stuff. So, do we have any more questions? Sorry.
We'd love to have some students participate, because the research is just fascinating.
Absolutely. Yeah. So do we have any questions? Any more? If not, then let's thank Bruce again and Rob for for their time and effort in putting this together. And this is very exciting. Thank you so much again. And
Thank you for
next
hosting
session
us.
will be next Monday. Yeah. Thank you, Bruce. Thanks.
Bye-bye.
Yeah. Bye-bye.